Welcome, everybody. My name is Steve Smith, aka R. Dallas. I'm a co-founder of NimblePros. We're a boutique consulting company focused on helping developers and development teams build better software faster. In this video, I'm going to share some of my experience with using distributed caching with Redis, and specifically how to scale it. This video is sponsored by ScaleOut software. I've known the folks behind ScaleOut software for probably 20 years. They're extremely smart, and we're going to learn a bit more about their product and how it compares to Redis later in this video. Now, imagine you're working with a simple web app that talks to a back-end database. As time progresses, the app is gaining popularity, but load is beginning to slow down the application. Caching is a great way to boost performance and scalability, so naturally you consider introducing a caching service like Redis. Getting started with a single Redis instance is pretty straightforward. Just SSH into your Linux instance and run the following commands to get up and running. Now the Redis instance is set up so that the web app can talk to it directly and only needs to go to the database if an entry isn't found in Redis. Queries made to the database are stored in Redis, so they will be available the next time a similar request is received. Of course, to really increase in scale, it can help to scale things out horizontally, adding a load balancer into the mix. In this scenario, 3 separate web nodes are established, and each one has its own corresponding Redis server. We're basically taking the original configuration and just multiplying it by 3. Unfortunately, in this case, while performance and scalability are both better, there's no consistency between the web apps. Each one of their separate caches may now hold different versions of the source data from the database. And without implementing something like sticky sessions, which can hurt scalability, users are going to see inconsistent results as they make subsequent requests that are fulfilled by different web apps and their separate Redis caches. Having separate caches with no synchronization between them is a recipe for confused and unhappy users. We don't want separate requests, possibly triggered by the same page load, to return back different versions of cached data. Fortunately, Redis supports clustering. Our new goal is to modify our architecture so that all of the web apps share access to a single Redis cluster. We're going to take our 3 existing Redis servers and turn them into a single Redis cluster. We're still getting the scalability benefits of having multiple Redis servers, but by using a cluster, we are ensuring different versions of the data aren't being stored separately and potentially becoming out of sync. So let's get this set up. Redis has docs on scaling Redis using Redis Cluster. In fact, the docs are simply called scaling in the URL. We need to think about what ports Redis will be using. The main port is 6379, which is the standard Redis port, and the same thing we were using before moving to a cluster. The cluster bus port is new though, and we need to make sure it's open for the Redis instances to communicate with one another. Redis clustering uses a technique called data sharding. Clusters have 16,384 hash slots, and every key is assigned a hash slot deterministically using the CRC16 algorithm. Each node in a cluster is responsible for a collection of hash slots, and as nodes are added or removed, the mapping of hash slots to server nodes must be updated. Redis clusters should use replicas to ensure data integrity in the event of a node failure. Every master node should have at least one replica node. This way, if the master node dies or is unavailable, there is a replica available that can be promoted to master, allowing the cluster to continue operation. CAP theorem applies to Redis clusters. CAP theorem states that distributed systems must choose 2 out of the 3 guarantees. The system can remain consistent, available, or partition tolerant, but not all 3. If you're watching this, you may also be interested in how CAP theorem applies to microservices, so check out the related article linked here. It'll be in the video description as well. Redis cluster chooses not to guarantee strong consistency because of the performance impact it would have. Therefore, it's possible that due to a network partition, Redis may return out-of-date data. Redis chooses availability over consistency during network partitions. The docs describe exactly how Redis could lose writes as a result of their lack of consistency guarantees. Essentially, if a network partition occurs, leaving the client with access to a minority of instances that includes at least one master, that master may receive a write, while in the meantime, its replica is promoted to master on the majority side of the partition. If the network is then restored, the master in the majority will be kept, and writes that were sent to the one in the minority are lost. As long as we're okay with this possibility, we're good to go. Personally, I typically use Redis as a cache, and as long as it's just a copy of the real data, which is persisted somewhere else, I'm not too worried about whether writes are out of sync or lost, because I can always get the data again from the source. But I recognize this isn't true of every Redis use case, and if you're using Redis to store real data, for instance, shopping cart data, you absolutely don't want that data to be lost due to a lack of consistency. All right, so let's go ahead and create a Redis cluster out of our 3 individual Redis instances that we already have. First, we're going to review the documentation. The first thing it says that we need is an empty Redis instance running in cluster mode. Well, great, we have our 3 instances. Apparently, we just need to configure these settings. Oh, and if you end up needing it, the flush all command will empty a Redis instance so you can perform the clustering operation on it, assuming you're okay with losing whatever data is on it. Wait a minute. The docs say that the minimal cluster that works as expected must contain at least 3 master nodes and is strongly recommended to include 6 nodes total. I wasn't expecting that at this point. I thought 3 servers would be more than enough, but it turns out we're going to need more servers, so things just got a little bit more expensive. That's all right. We'll go buy or provision some more resources. We'll just crank up some more VMs in our cloud provider. And all right, much later, after we've done all that, and we've gotten approvals and we've set up these things, we're ready to set up the cluster again. All right, so now we need to SSH into each server. Now we have 6 of them. And we need to confirm the settings in redis.conf match the ones that we just saw in the docs. Now for new servers, we're going to need to provision Redis using the commands shown here to actually install Redis tools and Redis server. This all honestly takes a while, and it is kind of tedious. It's probably more tedious to do it than to just watch, but I'll let you watch here for a moment just so you get a sense of what's involved. Doing it one time is no big deal, but doing it over and over again on multiple different machines can get to be pretty painful. Like you are just bored out of your mind and want to do anything else but this. If you can automate this and you think you might be doing it more than once, you probably should. But in my case, the total number of commands and the number of nodes was just small enough that it didn't seem worth automating. Remember, you're going to need to do this on every server. Much later, we have 6 of these nodes up and running with SSH going to each one, and Redis is installed. Huzzah! Also, this got me to install Windows Terminal since it has tabbed instances, and dealing with 6 individual windows was obviously getting rather painful. All right, so now we're actually ready to make a cluster. We can use the CLI from any of the nodes using the command shown here. Note that cluster replicas 1 at the end of this command ensures that there will be 1 replica for each master. In this case, I have a total of 6 servers that I'm listing, so we're going to end up with 3 masters and 3 replicas. Of course, nothing works on the first try, so the very first problem that we run into is connection refused. It turns out that even though the docs don't mention it anywhere, by default Redis servers run in protected mode. They'll work fine from localhost, but they won't actually accept any remote requests until you disable protected mode and then restart the server. Restarting the server requires you to go into /etc init.d and then call Redis server restart. Now you have to do this for every node, so 6 times. If you were previously already using 3 of those nodes, like we're saying we were here, those ones are probably already set correctly. It'll just be the new ones you're adding for your replicas that will need this change. All right, so after we do this, we should be good to go. Oh, wait, there's also this. We have to also not bind to localhost 127.0.0.1. So in addition to protected mode being off, you also need to comment out this line since it also has the effect of making Redis only work from localhost. Again, if you were already using Redis servers, they probably have this commented out already, but any new ones will need to have this change. So go and fix this a bunch of times on a bunch of different servers, edit each config file and save it ad nauseum. All right, now the total number of changes which we had to make to Redis conf to get this to work was to add a comment, change the values of protected mode, also make append only yes, that was in the docs, then uncomment cluster enabled, make sure it's set to yes, make sure you have a cluster config file, and set the cluster node timeout. As we go and we change those things one by one, we can see that the connection refused moves on to the next node and the next node until finally we are able to set up the entire thing. And it will describe to us how it thinks that it wants to configure things. It's going to show us which of the nodes are going to be masters, which slots are going to be assigned to each master, and which replicas are going to replicate which master nodes. If everything looks good, you can type yes to proceed. At this point, my new Redis cluster looks like this. I'm showing the last 3 digits, or at least the last octet of each IP address. At the top, you have the 3 masters and which slots they're holding. And at the bottom, we have our 3 replicas. Notice that the hash slots are roughly the same. They're balanced between the masters, and they're in ascending order in large contiguous blocks, which is kind of nice. It's what you would expect. All right, so we can actually confirm all of this and see the most important line here saying, okay, all 16,384 slots are covered. We can also go and ping our cluster to make sure that it's working, and you can test it to see how it works with various keys. However, the set operation only works if you're talking to the master node where the hash slot resides for that key, assuming that you're just using the base Redis CLI. If your key slot is on another node, you'll get an error letting you know which node that slot is on, but the operation won't complete. In the CLI, it's up to you to get the data there. In most API clients, the client should handle getting the key to the right node for you. Note that in this case, I'm connected to the IP ending in .199, which is a replica node. So any command I send is going to result in a moved error like the one you see here. Note that you can avoid this by running the Redis CLI in cluster-aware mode by passing it the -c parameter. Try different keys to get different hash sets. Some are going to be stored locally, and others are stored elsewhere. I'm connecting to one of the master nodes, which is node 157, and you can see that it contains the key for foo, its hash set, and for Zulu. But when I try and set a key Mike, it's going to tell me that that's actually on another server, masternode.247. Again, if you just pass in the -c parameter to your CLI, it'll be cluster aware and it'll figure out where these things go without you having to do it yourself. Now that we have a Redis cluster working, it's worth considering how it will fare in production. What are some important questions we might want to consider as we think about deployment and ongoing maintenance of the cluster? For example, what if we don't want to flush all the data in an instance when we're preparing to add it to the cluster? What happens to its data? And then what happens to the cluster when new nodes are added to it? Maybe initially 3 masters with 3 replicas is sufficient, but later we want to expand. Is there a simple command for that? Does it handle rebalancing the hash slots for me? Well, it turns out that the answer to the first question is pretty simple. You can't add a node to a cluster if it has data in it. You need to start with a fresh node or run flush all to remove all of the node's data. Only then can you add it. If you need to migrate the data, you'll need somewhere to hold the data so that after adding your node to the cluster, you can migrate the data into it. More servers will be needed. Alternately, you may be able to migrate from your new instance to an existing cluster prior to adding the instance to the cluster. In any case, everything is simpler if you don't need to keep any of the existing data. Once you add nodes, they don't immediately get any hash sets. You have to do that yourself. So if you look at this cluster info screenshot right here, I've just added a node and a replica to the cluster. And so you can see that the cluster known nodes is 8. However, the size of the cluster size, is only 3. And the reason for that is that it's not actually using any of the servers that I've just added. What's going on here? Well, it turns out that there is a CLI command that is just for this purpose, and you just need to run Redis CLI -- cluster rebalance and target one of the nodes in the cluster. Unfortunately, after you run this command, it actually doesn't do anything, and it will just come back and tell you, hey, cluster's already balanced. It turns out that you have to know an extra flag in order to make it do the right thing, and that is called use empty masters. If you tell it to rebalance and you specify cluster use empty masters, it will see the new empty node that you've just added, and it will realize that, hey, that could be pulling some of its own weight, and it will migrate a bunch of the nodes from the existing masters to the new empty master. You'll see something like this as it moves those slots. It'll take a few moments. However, after rebalancing, your slots may be extremely non-contiguous. There's not really a significant performance impact because of this, but it does make the CLI a lot more tedious to use, because instead of seeing something like, hey, I'm going to cover all the hash slots from 0 to 5400, you're going to see something like this inside of all of your info tools that you're going to use from the CLI. I'm not aware of a simple fix for this problem other than completely nuking your cluster and starting over with the number of nodes you want it to use. In this case, it would be 8 instead of the 6 that I was trying, because I'm rebalancing to add an extra master and replica. Turns out that nuking the cluster and restarting from scratch isn't actually all that easy. There's no command to do that. There's not a command to like just reset everything back to the way it was when you started, but I'll show you a little bit on how I made that work at the end of this video. What about the reverse operation? What if we need to remove a node and we need to rebalance the nodes that are left, essentially going back to a 3-master, 3-replica cluster from the 4-4 cluster we have now? These should be pretty standard operations for cluster management, and you would expect that Redis Cluster would support them. The CLI has a command to remove a node that you can send to any cluster node with the ID of the node to remove. However, it doesn't work unless it is empty. Just like adding a node to a cluster, nodes must be empty in order to be removed. Now, you can just run flush all if you don't care about any of the data on that node, but it's probably better for you to go ahead and reshard that data to other nodes. Unfortunately, doing so is usually a manual process of hash slot by hash slot, but you can automate it with a script. There's also a cluster forget operation, but it must be applied to all of the nodes quickly in order for it to work. So again, you would probably want to script this as well. Stack Overflow has various answers to these questions of how to do these operations. There are scripts available that will let you migrate hash slots between nodes. I didn't find these scripts in the documentation, so you have to rely on the community to come up with these scripts, because the CLI only supports very low-level, one item at a time operations. Rather than trying to migrate the data from one node to all 3 of the remaining nodes, it's simplest to just migrate all the data from one to another, and then you can rebalance. So in this case, if I had 4 nodes, I could take everything on node 4 and move it to node 3. Now node 3 is going to have twice as many nodes as 1 and 2. It's out of balance. So we're going to want to run cluster rebalance in order to make sure that they are now distributed evenly once again, with each one having about 1/3 of the hash slots. Now, what if a node just dies? Right? If you're worrying about having a cluster with replicas, you've probably considered the possibility of what happens when a service fails. It's worth testing this out to see what happens. You can kill a master node by simply stopping it from the command line. If it has a replica, that replica should then be promoted to master, and the cluster will remain healthy. However, if you then turn around and kill the new master while no replica exists, the cluster will fail. Any attempt to communicate with it will be refused. Your Redis cluster is only as resilient as the number of masters and replicas it has. This isn't surprising behavior. It's exactly how Redis clusters are designed to work. This is why we have replicas, is so that the cluster can remain resilient up to a certain number of failures. Okay, so let's review. We started with 3 Redis instances, and we rightly decided that it would make more sense to merge these into a cluster. However, pretty much immediately, we found out that really we'd need twice as many servers if we wanted to have any redundancy or follow Redis's recommendations for how this environment should work in production. So we had to spend more resources to spin up more servers or virtual machines or whatever we're using. The process of configuring the Redis nodes to work as a cluster was tedious at best. It required a lot of manual changes to config files on every one of the 6 nodes involved. Eventually, and with much Googling and help from Stack Overflow, it all worked. Recall, though, that administering the cluster also required very fine-grained operation through the CLI, and there weren't operations available for larger things that you might want to do. Adding a node was not just a process where you could just add it and it would rebalance automatically. No, we had to add it and then perform that operation ourselves and make sure we had all the right flags and stuff set to do it. One thing you should note is that you can host replica Redis instances on the same server as the masters. In fact, one of the things the doc shows, which is not something you should do in production, is installing 6 copies of Redis on one server, each one on a different port. So you can certainly have side-by-side instances of Redis on a machine, but you're not really getting that much redundancy if that machine goes down. So keep that in mind. Now let's switch gears for a moment and talk about ScaleOut software. ScaleOut has a product called ScaleOut StateServer, and StateServer is an in-memory database that has integrated Redis support, meaning you can set it up on your server and your existing Redis client apps can continue to connect to it as if it were Redis. There are no changes required on the client. You can also use a separate dedicated client, of course, but if you're already happy with Redis or if you have legacy code that depends on Redis and you don't want to touch it, you can just use this as a drop-in replacement. ScaleOut's in-memory database automatically handles clustering for you, so you don't need to deal with all the minutiae we saw with setting up a Redis cluster. It also has built-in patented high availability that doesn't require you to double your spend on server instances. Let's check it out for comparison's sake. First, we need to install the SOSS service on 3 of our Linux machines. Installation is pretty straightforward. First, you need to get the installer file from ScaleOut's website. Then we can send the file to the server using SCP or wget or whatever tool you want to use. And then last of all, you just need to install the file. Installing the file looks something like this. This is all covered in the documentation from ScaleOut. And when you run this, you should see something that looks like this. We depackage the actual installer file and it will read the thing and unpack it. And then after that, it installs the various services and it starts the ScaleOut grid service and the management REST API service. So everything is ready to go as soon as you run the installer. I'm installing SOSS on the same nodes that I've been showing Redis running on. By default, StateServer runs on port 721. And you can see here that it's acting as a separate Redis instance. I'm using the Redis CLI on port 721 to communicate with the brand new ScaleOut StateServer instance that I've installed. And when I set a key of our Dallas and give it a value of Steve, it shows me that it's redirected. Again, because I'm using the -C for cluster aware in the CLI this time, returns back OK. And when I say get, I get back the value that I just set, as you would expect. For comparison, running Redis CLI on the default port of 6379 continues to talk to the Redis cluster I set up previously on this same machine. For a better test and comparison, we can run some benchmarks using a .NET Console app. .NET Core doesn't come installed by default on these Linux machines, so first we'll need to install it. It's pretty easy to do using wget and the installer script that you can pull down from .NET. Next, you can just create a console app directly on the server if you like, using .NET New and your editor of choice. You can also use Git as an easy way to pull source code onto one or more nodes. Shown here is an initial prototype of just connecting to ScaleOut using the ScaleOut client. For the very simplest test, just use .NET Run, and then you can use SOSS Query to see stats on the StateServer in-memory database cluster. Notice that we didn't need to deal with hash slots or any of that stuff. Here you can see that we've added the one object, which was that key that we created up above. Now, we also want to ask similar questions about ScaleOut StateServer to what we did with Redis. One of those questions is how many nodes are needed? In this case, we only need to use the nodes we want to use. 3 in this case, but 1 or 2 would work fine as well. Now, how can we verify that the data is balanced, like we had to do with Redis cluster? There's not really any need. The ScaleOut StateServer service does this automatically for us. What happens when one of the master nodes in this cluster dies? Well, the ScaleOut StateServer is self-healing, and it automatically rebalances in response to changes in the number of nodes, whether adding or removing. So we don't have to deal with hash slots ever. We don't have to worry about what to do when we add a node. We don't have to rebalance when we remove a node or something fails. All of that is handled for us automatically. In fact, ScaleOut state servers will automatically detect and recover from the loss of a node. And so there's constantly this heartbeat check that's running between the nodes so that they can verify that the cluster is in a good state. If one of the nodes suffers a partition, it will automatically take one of the existing replicas, promote it to master, and rebalance if needed so that the workload can continue to be served. Unlike Redis, where we had to configure separate Redis servers as masters or replicas, every ScaleOut StateServer service includes within it the primary hash slots, the replicas, and the load balancer. So as a user of this service, you don't have to manually deal with hash slots or balancing or any of that. The service does it all for you because that's part of its job. And it's far more likely to do it consistently and correctly than you are. Self-healing also means that you don't have to detect when something goes wrong and then do something about it immediately, whenever that might be. If you need to be on call when your cloud-based infrastructure starts to fail and notifications are going to be sent and you've got pager duty, you're going to be much happier if you have a service that is self-healing than if you have one where you're going to have to get up at 3 o'clock in the morning and try and coherently run the right scripts to move the cluster into a better state. Now, after getting all this set up, I ran some benchmarks to test the performance of the two clusters compared to one another. I used benchmark.net, which I hadn't used much before. Among other things, I learned that you can't simply pass command line arguments into your benchmark services to control parameters. Instead, you must use environment variables, which can still be set on the command line, as you'll see in a moment. The benchmark services for both Redis and SOSS follow the same steps. First, they connect to the cluster with the appropriate client. Then, they perform write count write operations. Each write operation writes payload bytes of data to a cache entry. After each write, the client performs read ratio read operations. So those are the three main variables that I use to control these benchmarks: the write count, the payload bytes, and the read ratio, the number of reads per write. This is one of the write and read methods used for the benchmark. The outer loop is for the writes. The keys are all just GUIDs. And the payload is configured based on byte size. It's actually going to read a number of bytes from a War and Peace book text file and then take that as the payload that it's going to store. Then there's an inner loop that performs the reads. There also is some logging, but that's disabled by default so that it doesn't impact the performance overly much. All right, so first we're going to show what Redis cluster's performance was. We're going to do 10 writes for each iteration, 100 reads per write. We're going to assume that this data is fairly cacheable because we're actually caching it. And we're going to have a payload size of 20,000 bytes. So not exactly 20 kilobytes, but 20,000 decimal bytes as our payload size. When we do this, Redis comes up with an average of about 296 milliseconds to perform these operations. Now, these benchmarks were run from another node in the same network as the cluster, but not one of the cluster machines. We're going to run the exact same settings on the SOSS cluster, which is running on 3 of the same machines that Redis is running on. So it's exactly the same hardware, literally the same servers. And we're going to do 10 writes, 100 reads per write, 20,000 byte payload. And at this point, SOSS is able to perform 162 milliseconds on average. So if we do a quick comparison between the two, you can see that the Redis benchmark, 296 or so milliseconds, was 82% slower than the SOSS one at 162 milliseconds on average. But the SOSS client does have some built-in client-side caching that I'm not aware of the Stack Exchange Redis client having. So maybe that's tipping the scales, since we're doing so many reads for every write. Let's run it again, but this time let's do only one read for every write. You can see that this benchmark averages just 46 milliseconds for Redis. Obviously much faster than we had before because we're not doing 100 reads for every one of these writes, okay? Likewise, we're going to do the same thing using ScaleOut StateServer Exact same settings, exact same hardware, 20,000 byte payload. And here I was surprised to see that it is averaging just under 9 milliseconds. And so it is significantly faster than it was before. I expected that because the caching would be out of play, that they would be a lot closer to one another. Certainly did not expect for the difference to get greater in this case. So comparing the two, you can see in this case, Redis is about 5.5 times the time, 4.5 times slower than ScaleOut StateServer. Now, you may not care too much about an average 38 milliseconds difference in your request, but it can add up, especially if you need to make multiple requests to the cache within a given web request. Also note that this is with SOSS only running 3 instances, not 6, which is what Redis is using, and also SOSS is providing consistency guarantees that Redis is not. So I just mentioned consistency. Let's go back to that. Remember, Redis does not make any claims to ensure strong consistency. Their docs demonstrate exactly when and how data will be lost using Redis Cluster. SOSS ensures consistency in the face of node partitions. There are scenarios where, because of the stronger consistency checks that SOSS has, Redis Cluster outperforms SOSS. But in these cases, if StateServer is configured to not enforce consistency, which is a flag that you can set, it does again outperform Redis Cluster. At that point, it's more of a fair contest, and StateServer continues to outperform Redis when they're on the same playing field. All right, now here's a quick bonus content for those of you that want to do your own tests. It can be very valuable to be able to remove a cluster that you've just configured for Redis, and you don't necessarily want to re-provision the VMs from scratch in order to wipe them clean. You just want to be able to take your Redis instance that already has the software installed on it and take it out of the cluster, and then be able to add it back to the cluster and have everything start fresh, right? And so if you try and do that by just setting cluster enabled to no, and then joining the cluster again, you'll find that all the same logic that was in the cluster before, for instance, if your hash slots are extremely fragmented, that's still going to be the case. And so the extra thing you need to do is you need to find the cluster config file. And so to do that, it's probably going to be in the same location you see here. But if you can't locate it, you can run this find command to look for that file. In my case, it was 6379.conf. And with that, you'll be able to find your nodes-6379.conf or whatever yours is called in whatever folder. And once you delete that config file, then you're able to set cluster config to no, flip it back to yes after you've killed the cluster, and then recreate the cluster. So here you can see that I was able to recreate a cluster by taking the 3 nodes that I had before, removing their cluster config file, setting them to no, and then saving everything and restarting everything, then setting them back to yes, rejoining the cluster. And you see now the slots are contiguous like they were before. So everything's a lot cleaner and easier to work with in the CLI tools. All right, I hope you found this helpful. I have some resources that I found useful while I was working on this. I'm just going to throw them up here. You can hit pause on the video and copy them down if you see anything that you think would be interesting. I have even more resources and a full write-up of this available on my blog. I'll have a link to that inside the description. With that, thanks a lot for watching. If you enjoyed this video, please go ahead and hit the like button. You can also subscribe if you want to get notified when we have new content from NimblePros. Until next time, keep improving.